The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So this is the outline of the lecture for today. So we just need to talk about the conditional densities for Poisson process. So these are the things that we've seen before in previous sections. So I'm just going to give a simple proof for them and some intuition. So if you remember the Poisson process, so this was the famous figure that we had. So at time instant 0, n of t was 0. And then we had some arrivals. So at time instant t, we had n of t arrivals, which is equal to n. And this is Sn. Yeah, so this is the figure that we had. So for the first equation, we're looking at the, so we want to find the conditional distribution of inter-arrival times condition and the last arrival time instant. So first of all, we want to find the joint distribution of the inter-arrival times and the last arrival. So this equation. So you know that inter-arrival times are independent in Poisson process. So just looking at this thing. You know that these things are independent of each other. So I will have lambda to the power of n e to the power of minus lambda. And then this last one corresponds to the fact that xn plus 1 is equal to n plus 1 minus summation of x. You know, these two events are equivalent to each other. So this is going to correspond to lambda e to the power of minus lambda. So we just do it the other way. So it's going to be like so you know it's just bad. So you can just get rid of these terms, and it's going to be that equation. So it's very simple. It's just the independence of inter-arrival times. So you look at the last term as the inter-arrival time for the last arrival, and then they're going to be independent, and the terms kind of cancel out, and we will have this equation. So this conditional density will be the joint distribution over the distribution of Sn plus 1, which is like this. So so this joint distribution will be like this. So what is the intuition behind this thing? This means that you've seen this term before. This means that we have uniform distribution over the interval of 0 to 1, condition on something. So previously, what we had was the conditional distribution of arrival times condition on the last arrival. So f of S1 to Sn condition on Sn plus 1. But here we have distribution of x1 to xn condition on Sn plus 1. And previously, the constraint that we had was like we should have ordering over the arrival times. So because of this constraint, we had this n factorial, if you remember, that order statistics things that we talked about. Now here what we have is something like this. So all the inter-arrival times should be positive, and summation of them should be less than t. Because, well, you know that summation of them to n plus 1 is equal to Sn plus 1. So, and the last term is positive, so this thing should be less than t. Yeah, so these two constraints are sort of dual to each other. So because of this constraint, I had some m factorial over the conditional distribution of arrival times condition on the last arrival time. Now I have inter-arrival conditional distribution of inter-arrival times condition on last arrival time, and we should have this m factorial here. So the other interesting thing is that if I condition it on the n of t, so the number of arrivals at time instant t, the term is going to be very similar to the previous one. So just to prove this thing, it's very simple again. Yeah. So I just want to show you. So what does this thing mean? This thing means that these are the distributions of the inter-arrival times, and the last event corresponds to the fact that xn plus 1 is bigger than t minus summation of xi. Because we have an arrival time at Sn n, and then after that there is no arrival because that at time instant t we have n arrivals. So this corresponds to this thing. So again we will have some term like lambda n e to the power of. This is for the first n events, and you see that these are independent because of the Poisson properties of the Poisson process. And the last term will be, so you know, probability of a Poisson random variable bigger than something is yeah. So these thing cancel out. And then we will have this term, this first term lambda to the power of n. Just forget about n plus 1. And probability distribution of n of t equal to n is this term without n plus 1. So lambda n to the power of n e to the power of minus lambda t over n factorial. So those terms cancel out, and we will have this thing. So again, we should have this constraint set that summation of x k equal to 1 to n should be less than t. So, yeah, I mean, no matter if we are conditioning on n of t or Sn plus 1, the last arrival time or the number of arrivals at some time instant, the conditional distribution is uniform, subject to some constraints. Is there any question? So if we look at the limit, and so again looking at this figure, you see that this is correspond to Sn plus 1, and you see that Sn plus 1 is bigger than t. So if we take the limit and take the t1 going to t, these two distributions are going to be the same. So T1 corresponds to Sn plus 1. T1. Yeah, so basically what it's saying is that conditional distribution of inter-arrival times are uniform, independent of what is going to happen in future. So in future, there might be some, I mean, the knowledge that we have about future could be the fact that no arrival happens in this interval, or the next arrival is going to happen at some point. I mean, condition on these things, the inter-arrival times are going to be uniform. Yeah, the other fact is that this whole the distribution that I showed you, they are all symmetric with respect to inter-arrival times. So it doesn't matter. I mean, no arrival has more priority than to any other one, or they're not different to each other. So, and if we look at the permutation of them, they're going to be similar. So now I want to look at the distribution of x1 or S1. They're equal to each other. So I can easily calculate the probability of x1 bigger than some tau condition on, for example, n of t is equal to n. So what is this conditional distribution? So condition on n of t equal to n, I know that in this interval, I have n arrivals and in n inter-arrival times. And I want to know that if x1 is in this interval. So, or S1 is equal to x1. And you know that SIs are also uniform. So you know that these are independent of each other. And so you can say that the condition, the probability of this thing is like this one. So all of them should be bigger than tau. And since this is symmetric, so this corresponds to x1. Since this was, I mean, everything was symmetric for all inter-arrival times, this is also the complementary distribution function for xk. Is there any question? So the other thing that are not in the slides and I want to tell you is the conditional distribution of Si given n of t. So I know that there are n arrivals in this interval. Sorry. I don't want to see if the ith arrival is somewhere like this. So the probability that, I mean, so this event corresponds to the fact that there is one arrival in this interval, and I minus one arrivals here, and n minus I minus one arrivals here. Oh, no, sorry, n minus I arrivals here. So the probability of having one arrival here corresponds to, since the arrival times are uniform, and I want to have one arrival in this interval, it's like this. And I want to have I minus arrivals here, and n minus one, and n minus I minus one arrivals here, and n minus I arrivals here. So it's like a binomial probability distribution. So out of the n minus one remaining arrivals, I want to have some of them in this interval and some of them here. So this is the distribution of this thing. Yeah. So just as a check, we know that the last arrival time, the distribution of that thing is here. You just cancel out these things too. Is we're going to get back to this equation. But it's just the same as this one, but you let I equal to n. Is it okay? Just setting I equal to n, get this one.
Does this equation also apply to I equals to 1?
Yeah, sure. So yeah, I equal to 1, we will have n t minus tau and if you look at this thing, And so this is the complementary distribution function. You just take the derivative, you get that one. Right? Yeah, this is just a check of this formulation, you know. So, yeah. So is there any other question? Did anybody get why we have this kind of formulation? It was very simple. It's just a combination of a uniform distribution and a binomial distribution. So tau is this thing. I made a mistake. Tau is the SI. So change of notation. I said that I want one arrival in this interval, and I minus one arrivals here, and n minus I arrivals here. So I define a Bernoulli process. So probability of falling in this interval is tau over t minus tau. And I say that, OK, so falling in this interval in a uniform distribution corresponds to success. I want among n minus 1 arrivals, I minus one of them to be successful and rest of them to be fail. So I minus one of them should fall here and rest of them should fall here.
So that's equal to?
Which?
So that's the
Yeah. You just get rid of this dt and that's it.
Why the first term is n over t?
Which one?
Can you explain again the first term? The first term there, n dt over t.
Oh, OK. So I want to have one interval definitely here. But among among n arrivals, I want one of them to fall here, you know. So any one of them can fall. But then I minus one of them should fall here, and n minus I of one of them should fall here. Any other question? It's beautiful, isn't it? So yeah. So there's a problem. OK. So I studied. So you all saw this thing. So I studied x1 to xn, but what is the distribution of this remaining part? So if I condition on nt or condition on sn plus 1, what is the distribution of this one, or you know, or joint distribution of all these? So this is what we are going to look. So first of all, if I do the conditioning over sn plus 1, and I find the distribution of I find the distribution of x1 to xn condition on sn plus 1. Is there any randomness in distribution of xn plus 1? So this is going to be xn plus 1. So this is going to be xn plus 1. So if I find the distribution of x1 to xn condition on this condition on sn plus 1, you know, I mean, it's very easy to show that xn plus 1 is equal to sn plus 1. So there's no randomness here. But yeah, but looking at the figure, you see that and the distributions, you see that everything is symmetric. So I found the distribution of x1 to xn, and I can find xn plus 1 easily from them. But if I find the distribution of x2 to xn plus 1, condition on this thing, and then find x1 from them, you know, you can say that x1 is equal to xn plus 1 minus 2 to n plus 1 xi. You know, we have this formulation. So it seems that there's no difference between them, and actually there's not. So condition on Sn plus 1, we have the same distribution for x1 to xn or x2 to xn plus 1. But there are only n free parameters because the n plus 1 can be taken, I mean, can be calculated linearly, you know, in linear equations. So yeah, so if we take any n random variables out of this n plus 1 random variables, we have the same story. So it's going to be uniform over 0 to t, over this interval. So it's symmetric. Now, the very nice thing is about n of t equal to t. So the n of t equal to n. So, so this was easy because we had these equations. But what if I call this thing x star of n plus 1, and I do the conditioning over n of t? You know, so I don't know the arrival time for n plus 1th arrival, but I know the number of arrivals at time instant t. Condition on that, what is the distribution, for example, for x star n plus 1 or x1 to xn? So again, easily we can say that it's the same story. So it's uniform. So you can take out of x1 to xn and x star n plus 1, you can take n of them and find the distribution of that. Or the other way, okay, so the other way to look at it is that if I find the distribution of x1 to xn condition on n of t, I will have this fact that x star n plus 1 is equal to t minus Sn, which is t minus summation of xi. Can everybody see this? Hope so. Oh, okay, yeah, it's better. So again, if I find the distribution of x1 to xn, I can find x star n plus 1 deterministically. So just as a sanity check, you can find that f of f star of x, oh sorry, f of x star n plus 1 condition on so looking at this formulation and just replacing everything, you can find this thing. And you can see that this is similar to this one again. So this is the distribution for, well, this is the distribution for x1, so you can find the density. And this is going to be density. So what I'm saying is that x1 has the same marginal distribution as xn plus 1 star. So you can get it with this kind of reasoning, saying that the marginal distribution should be the same. Or looking at this kind of formulation. So when you have this distribution, you can find the distribution of summation of xii equal to 1 to n, you know. And then you can find, so t is deterministic, so you can just replace everything and find it. And you can see that these two are the same.
So the conclusion that xn plus 1 star are the same distribution that x1?
Yeah. Condition on nt equal to n. Yeah, so everything is symmetric and uniform. But you can only choose n free parameters because the n plus 1 is a linear combination of the n. Right? Yeah, so this is the end of the chapter corresponding for Poisson process. Is there any problem or any question about it? So let's start the Markov chain. So in this chapter, we only talk about the finite state Markov chains. So Markov chains are some processes that change in integer time instants. So it's like we are quantizing time, and any kind of change can happen only in integer time instants. And it's different in this way from Poisson processes, because we can change the Poisson, I mean, we can have the definition of Poisson processes for any continuous time, but Markov chains are only defined for integer times. And a finite state Markov chains is a Markov chain where the states can be only in a finite set. So we usually call it 1 to m, but you can name it in any way you like. So yeah, okay, so what we are looking for in finite state Markov chains is the probability distribution of the next state condition on whatever history that I have. So I know that at integer times there can be some change. So what is this change? We model it with the probability distribution of this change corresponding to the history. So we can model any discrete integer time process in this way. Now the nice thing about Markov chains or homogeneous Markov chains is that this distribution is equal to these things. So you see I and j, so I is the previous state and j is the state that I want to go in. So the distribution of the next state condition on all the history only depends on the last step. So given the previous state, the new state is independent of all the earlier things that might happen. So there's a very nice way to show it. So in general, we say that xn plus 1 is independent of condition on xn plus 1. Oh, sorry. Yeah. So if I know the previous, and these things are true for all the possible states. So whatever the whatever the history and the earlier process that I had, I only care about the state that I was in previous time. And this is going to show me what is the distribution of next state. So the two important things that you can see in this formulation is that, first of all, this kind of independence, where it is true for all I, j, k, m, and so on. The other thing is that it's not time dependent. So if I am in some state, the probability distribution of my next state is going to be the same if the same thing happens in 100 years, So it's not time dependent. That's why we call it homogeneous Markov chains. And we can have non-homogeneous Markov chains, but there are not many nice results about them. We cannot find many good things. And all the information that we know to characterize a Markov chain is this kind of distribution. So we call these things transition probabilities. And something else which is called initial state or initial probabilities, which tell me that at time instant 0, what is the probability distribution of the states. So knowing Markov chains, you can find that probability distribution of x1 is equal to probability of x1 condition on x0 times. So knowing this thing and these transition probabilities, I can find the probability distribution of x1. And then, well, very easily, probability of xn is equal to, sorry. So you can do this thing iteratively. And by just knowing the transition probabilities and initial probabilities, you can find the probability distribution of the states at any time instant up to forever. You see, it's very easy. You just do this thing iteratively. So I called about the independence and initial. So what we do is we characterize the Markov chains with this set of transition probabilities and the initial state. And you see that these transition probabilities, we have m times m minus 1 free parameters in them, because the summation of each of them should be equal to 1. So for each initial state, I can have a distribution over the next step. So I'm going to talk about it in the matrix form. And what we do in practice, usually we assume the initial state to be a constant state. So we usually just define a state calling initial state, usually call it x0, and it's going to be, it's what you're going to usually see if you want to study the behavior of Markov chains. So, so these are the two ways that we can visualize the transition probabilities. So matrix form is very easy. So you just look at the m probability distributions that you have. So in a Markov chain with m and with m number of states, you will have m distributions, each of them corresponding to the conditional distribution of next step, condition, and the present step equal to I. So I can be anything. So this was the thing I was saying, the number of free parameters. So I have m distribution, and each distribution has m minus 1 free parameters, because the summation of them should be equal to m, to 1, sorry. So this is the number of free parameters that I have. So is there any problem with the matrix form? I'm assuming that we've all been seeing this sometime before. Fine. So the nice thing about matrix form is that you can do many nice stuff with them. You can look at the notes for them, and we will see these kind of properties later. But you can imagine that just looking at the matrix form and doing some algebra over them, we can get very nice results from the Markov chains, about the Markov chains. The other representation of the Markov chains is using a directed graph, in which each node corresponds to a state, and each arc or each edge corresponds to a transition probability. And the very important thing about graphical model is that there is a very clear difference between zero transition probabilities and non-zero transition probabilities. So if there is any possibility of going from one state to another state, we have an edge or an arc here. And if there's no, so probability of 10 to the power of minus 5 is different from 0. We have an arc in one case and no arc in another case, because there is a chance of going from this state to the next one state, even when the probability is 10 to the power of minus 5. Yeah. And OK, so we can do a lot of inference by just looking at the graphical model. And it's easier to see some properties of the Markov chain by looking at the graphical models. We will see these properties that we can that we can find by looking at the graphical model. So this is not really classification of states, actually. OK, so there are some definitions, very intuitive definitions here. So we call, so there's something called a walk, which says that this is an ordered string of the nodes, where the probability of going from each node to the next one is non-zero. So for example, looking at this walk, you can have the probability of going from 4 to 4 is positive, 4 to 1, 1 to 2, 2 to 3, and 3 to 2. So there is no kind of constraint in the definition of the walk. There should be just positive probabilities in going from one state to the next state. So we can have repetition. You can have, well, whatever we like. Yeah, and the number of, well, you can find the number of states for sure. So what is the maximum number of steps in a walk? Or minimum number of, OK, minimum number of states is 2, 1. So what is the maximum number of steps? Well, there's no constraint, so it can be anything. So the next thing that we look is a path. A path is a walk where there is no repeated nodes. So I never go through one node twice. So for example, I have this path 4, 1, 2, 3. You can see here 4, 1, 2, 3. And now you can say, what is the maximum number of steps in a path? Steps, not states. N minus 1, yeah. because you cannot go to one state twice. So you have maximum number of steps in one n-1. And the cycle is a walk in which the first and last node is repeated. So first of all, there is not a really great difference between these two cycles, so it doesn't matter where I start. And we don't care about the repetition in definition of cycle. So oh, okay, yeah, sorry. No node is repeated, so sorry, sorry, something was wrong. Yeah, we shouldn't have any repetition except for the first and last nodes. First and last node should be the same, but there's shouldn't be any repetition. So what is the maximum number of steps in this case? Yeah, because we have an additional step. So, yeah.
You said the path maximum number of steps is n-1?
Yeah.
Couldn't it be, I mean, if you have n equals, I think, 6, like you got there, could it be 1, 2, 3, 4, 5, 6?
No, it's the steps, not the states.
Got it.
So if I have a path from 1 to 2, and this is the path, so there's one state, one step. Yeah. Just whenever you're confused, make a simple model. It's gonna make everything very, very easy. Any other question? So this is another definition. We say that a node J is accessible from I if there is a walk from I to J. And by just looking at the graphical model, you can verify the existence of this walk very easily. But the nice thing, again, about this thing is what I emphasized in the graphical model, in which it talks about if there's any positive probability of going from I to J. So if there exists, if J is accessible from I, and you start at node I, there's a positive probability that you will end in node J sometime in future. There's nothing said about the number of steps needed to get there, or the probability of that, except that this probability is non-zero. It's positive. So, for example, if there's a state like K that we have P of ik is positive and P of kj is positive, then we will have P of ij2 is positive. So we have this kind of notation. I don't have a pointer. Weird. So yeah, we have this kind of notation. Pijn means that the probability of going from state I to state j in n steps. And this is exactly like n steps. So actually, this value could be different for different number of n. So for example, if we have a Markov chain like this, P of 1, 3, 1 is equal to 0, but P of 1, 3, 2 is non-zero. So node J is accessible from I if Pijn is positive for any n. So we say that J is not accessible from I if this is 0 for all possible n's. You see this?
Are those actually greater than or equal to?
No, greater. They are always equal to, they are always greater or equal to 0. Probability is always non-negative. So what I want is positive probability, meaning that there is a chance that I will get there. I don't care how small this chance is, but it shouldn't be 0.
Sorry, is it so P2ij though? Couldn't it be equal to Pik,
Yeah, exactly. Yeah. So in this case, P1, 3, 2 is equal to P1, 2, P2, 3.
So I guess I'm asking if P2ij should be greater than or equal to Pik, Pkj.
Oh, okay. No, actually, you know why? Because there can be some other state like here.
Right, but if that doesn't exist, so there's only one path, then it would be
Yeah, sure, but there's no guarantee. What I'm saying is that Pik is positive, Pkj is positive, so this thing is positive, but it can be bigger, you know. In this case, it can be bigger. I don't care, you know, I don't care about the quantity, about the amount of that probability. I care about its positiveness. It's greater than 0, you know. I just want it to be non-zero. The other thing is that when we look at Pijn, there's a chance. I mean, I don't care what kind of walk I have between I and j. You know, it's a walk, so it can have repetition, it can have cycles, or it can have anything. You know, I don't care. So if you really want to calculate Pij for n equal to, I don't know, 1,000, you should really find all the possible walks from I to j and add the probabilities to find this value. All the walks with n steps, you know. Now here, let's look at some examples. So is node 3 accessible from node 1? So you see that there's a walk like this, 1, 2, 3. So there's a positive probability of going to state 3 from node 1. So there's a walk. So node 3 is accessible from 1. But if you really want to calculate the probability, you should also look at the fact that we can have cycles. So 1, 2, 3 is a walk, but 1, 1, 2, 3 is also a walk. 1, 2, 3, 2, 3 is also a walk. You see, so you have to count all these things to find the probability of P1, 3, n, you know, for any n. What about the state 5? So if is the node 3 accessible from node 5? See that it's not. So if you go into if you go into state 5, you never go out. You know, with zero probability, with the probability of 1, you stay there forever. So no state except state 5 is accessible from 5. You know. So is node 2 accessible from itself? So accessible means that I should have a walk from 2 to 2 in some finite number, in some number of steps. So you can see that we can have 2, 3, 2, so, or many other walks. So it's accessible. But you see, as you see, node 6 is not accessible from itself. You know, if you are in node 6, you always go out. Actually, yeah, so it's not accessible. So let's go back to these definitions. Yeah, this is what I said, and I'm emphasizing again. If you want to say that j is not accessible from I should have a Pij n equal to 0 for all n. The other thing is that if there's a walk from I to j and from j to k, we can prove easily that there's a walk from I to k. So having a walk from I to j means that for some n, this thing is positive. So this is I to j. From j to k, this means that P of jk. For some m, this is positive. So looking at I to k, I can say that P of I to k m plus n is greater than. And I have this thing here because of the reason that I explained right now. Because there might be other paths from I to k, you know, except the walks going through j, or except the walks that have n steps to get to get to j and m steps to get to k. So we know that we can concatenate the walks from. So if there's a walk from I to j and j to k, we have a walk from I to k. Yeah. So we say that states I and j communicate if there's a walk from I to j and from j to I. So you can go back and forth. So it means that there's a cycle from there's a cycle from I to I or j to j, you know. This is the implication. So it's, again, very simple to prove that if I communicates with j and j communicates with k, then I communicates with k. You know, in order to prove that, I should assume that I communicates to j. I mean, I need to prove that there is a walk from I to k, and I need to prove that there is a walk from k to I. So this means that I communicates with k. So these two things can be proved easily from the concatenation of the walks and the fact that I and j communicate and j and k communicate. Now, what I can prove is, and what I can define is called something called a class of states. So a class is called a non-empty set of states where all the pairs of states in a class communicate with each other, and none of them communicate with any other state in the Markov chain. So this is the definition of class. So I just group the pairs that can communicate with the state, and just get rid of all those who do not communicate with it, and then it's you know, for defining a class, or for finding a class, or for naming a class, we can have a representative state. You know, so I want to find all the states that communicate with each other, you know, in a class. So I can just pick one of the states in this class and find all the states that communicate with this single state. You know, because if two states communicate with one state, then these two states communicate with each other. And if there's a state that, if there's a state that doesn't communicate with me, it doesn't communicate with anybody else whom I'm communicating with. I'm going to prove it now, just in a few moments. I want to look at this figure again. So first I take state 2 and find a class that corresponds to, that has this state in itself. So you see that in this class we have state 2 and 3 because there's only a state 3 that communicates with 2. And correspondingly we can have class having state 4 and 5. And you see that state 1 is communicating with itself, so it's a class by itself, but it doesn't communicate with anyone else. So we have this class also. So next question. Why do we call C4 a class? So it doesn't communicate with itself. Actually, it goes, if you're in state 6, you go out of it with probability of 1 eventually. So why do we call it a class? This is because actually, so this is the definition of the classes. But we want to have some very nice property about the classes, which says that we can partition the Markov chain, the states in a Markov chain, by using the classes. So if I don't count this case as a class, I cannot partition it, you know, because partitioning means that I should cover the whole states, you know, in the classes. What I want to do is to do some kind of partitioning in a Markov chain that I have by using the classes. So I can have a representative state for each class, and then this is the way to this is one way to partition the Markov chains. And why do I say it's partitioning? Well, it's covering the whole finite state space of the chain and the states. But I need to prove that there's no intersection between classes also. Why is it like that? So meaning that I cannot have two classes where there is a intersection between them. Because if there's any intersection, for example, I belongs to C1 and I belongs to C2, it means that I communicates with all the states in C1 and I communicates with all states in C2. So you can say that all states in C1 communicate with all states in C2. So actually, they should be the same. And there's only these states that communicate with each other. You know, we have this exclusivity, you know, the conditional. So yeah, we can have this kind of partitioning. Is there any question? Everybody's fine and good. So another definition, which is going to be very, very important in future for us, is the recurrency. And it's actually very simple. So a state is called recurrent if for all j that we have, for all the states that we have, j is accessible to I, we also have I is accessible to j. So if from some state I, in some number of states, I can go to some state j, I can get back to I from this state for sure. And this should be true for all the states in the class, in the Markov chain. So if there is a walk from I to j, there should be a walk from j to I too. If this is true, then I is recurrent. This is the definition of recurrence. Is it okay? And if it's not recurrent, we call it transient. And why do we call it transient? I mean, the intuition is very nice. So what is a transient state? Transient state says that there might be some kind of walk from I to some k, and then I can't go back. So there's a positive probability that I go out of state I in some way, in some walk, and never come back to it. So it's kind of transitional behavior.
Isn't the probability 1 that it'll exit and never come back?
No, with some probability. With some probability. So there exists some probability. So there's a positive probability that I go out of it and never come back. It's enough for definition of transiency. So you know why? Because I have the definition of recurrence for all the j's that are accessible from I. You know, so with probability 1, oh, okay, so I cannot say with probability 1. Yeah, but I cannot say probability of 1 for recurrency. But for transition behavior, I should have, I mean, there exists some probability. There is a positive probability that I go out of it and never come back. So just state 1 is transient. And state 3 is it recurrent or transient? Some idea? Transient? What about state 2? It's wrong because there should be something going out of it, you know. So now here it's recurrent. Good? Oh yeah, we have examples here. So states 2 and 3 are recurrent because the only state that I can go out from these two sets, I mean from this set, is to themselves. So they're only accessible from themselves, and there's a positive probability of going from one to the other. So they're recurrent. But states 4 and 5 are transient, and the reason is here. Because there's a positive probability that I go out of state 4 in that direction and never come back. Yeah, and there's no way to come back. And state 6 and 1 are also transient. State 6 is very, very transient because, well, I go out of it in one step and never come back. And state 1 is also transient because I can go out of it in this direction and never be able to come back. You see it? Nice. So this is the very, very, very important theorem, which says that if we have some classes, the states in the class are all recurrent or all transient. This is what we are going to use a lot in future, so you should remember it. And the proof is very easy. So so I define, so let's assume that state I is recurrent, and let's define Si, all the states that communicate with I, and that are accessible from I. And you know that since I is recurrent, being accessible from I means that I is accessible from them. You know, so if J is accessible from I is also accessible from J. So we know that I and J are communicate with each other only if and only if J is in this set. So this is a class. You know, this is the class that contains I. So this is like the class that I told you, that we can have a class where this state I is its representative, you know. And actually, any state in a class can be its representative. It doesn't matter. So by just looking at state I can define a class, the states that are accessible from I, and actually, they are the class that contain. This is the class that contains I. So let's assume that there's a state called K, which is accessible from some J, which is in this set. So K is accessible from J, and J is accessible from I. So K is accessible from I. But K accessible from I implies that I is also accessible from K, because I is recurrent. So you see, I is accessible from K. And you know that J is also accessible from I because, well, Si was the class, the recurrent class. So you see that J is also recurrent. So if K is accessible from J, then J is also accessible from K, for any K. So this is the definition of recurrency. So what I want to say is that if I is recurrent and it's in the same class as J, then J is recurrent for sure. And we didn't prove it here, but if one of them is transient, then all of them are transient too. So the proof was very simple. So what I said is that, I proved that if there is any state like K that is accessible from J, I need to prove that J is also accessible from K. And I proved it like this. It's easy. So the next definition that we have is the definition of the periodic states and the classes. So so I told you that the number of steps in a walk. So when I say that there's a walk from some state to the other state, I don't specify the number of steps needed to get from this state to the other state. So assuming that there is a walk from state I to I, meaning that I is accessible from I, you know, it's not always true. You might go out of I and never come back to it. So assuming that there's a positive probability that you can go from state I to I, you can look at the number of steps needed for this walk, and you can find the greatest common divisor of this number of steps, and it's called the period of I. And if this number is greater than 1, then I is called to be periodic. And if it's not, it's aperiodic. So the very, very simple example of this thing is this Markov chain. So probability of 1, 1 in one step is 0. Probability of 1, 1 in two step is positive. And actually, probability of 1, 1 for all even number of steps is positive. But for all odd number of steps, it's 0. And actually, you can prove that 2 is the greatest common divisor. So this is the very easy example to show that it's periodic. So there's a very simple thing to check if something is aperiodic, but it doesn't tell me. I mean, if it doesn't exist, we don't know its periodicity. So if there's a walk from state 1 or state I to itself, and in this walk we go from a state called like J, and there's a loop here. So Pjj is positive. What can we say about the periodicity of I? No, it's the period is 1. Yeah, exactly. So in this case, state I is always aperiodic. So if there's a walk, and in this walk there's a loop, we always say that. But if it doesn't exist, can we say anything about the periodicity? No. It might be periodic, it might be aperiodic. It's just a check. So whenever you see a loop, it's aperiodic. That's well, whenever you see a loop in the walk from I to I, if there's a loop in other side of the Markov chain, we don't care. So the definition is fine, isn't it? So just looking at this example. So for going from state 4 to 4, the number of states that we need is like 4, 6, 8. So 4, 1, 2, 3, 4 is a cycle, or is a walk from 4 to 4, and the number of steps is 4. 4, 5, 6, 7, 8, 9, 4 is another walk. So this corresponds to n equal to 6. And 4, 1, 2, 3, 4, 1, 2, 3, 4 is another walk, which corresponds to n equal to 8. So you see that you can go like this, or this, or this, So these are different n's. But we see that the greatest common divisor is 2. So the period of state 4 is 2. For state 7, we have this thing. So the minimum number of steps to get from 7 to itself is 6. And then you can get from 7 to 7 in 10 steps. And I hope you see it. So it's going to be like this. And so again, the greatest common divisor is 2. So we proved that but we proved that if one state in a class is recurrent, then all the states are recurrent. And we saw that recurrency corresponds to having a cycle, having a walk from each state to itself. You see? So this is the result very similar to that one, which says that all the states in the same class have the same period. And well, in this example, you see it too. The proof is not very complicated, but it takes time to do that, so I'm not going to do it. But it's sort of nice, so it's good if you look at the text to see that.
The period is not defined only for recurrent states?
Yeah. For non-recurrent ones, it's
Infinity?
it's 1. It's a periodic. I think okay, yeah. Periodicity is only defined for recurrent states. Yeah. We have another example here. I just want to show you. So I have two. I have 2 recurrence classes in this example. Actually, 3. So one of them is this class. What is the period for class corresponding to state 1? It's 1 because I have a loop. It's very simple. I can, for any n, there's a positive probability. What is the period for this class, states corresponding containing states 4 and 5? Now look at it. There's definitely a loop in this class, so it's 1. No, I said that whenever there's a loop, the greatest common divisor is 1. So for going from a state 5 to 5, we can go it in 1 step, 2 step, 3 step, 4 step, 5 step, you know. So the greatest common divisor is 1. So here I showed you that if there is a loop, then it's definitely aperiodic, meaning that the greatest common divisor is 1.
But
And
we didn't have self-transitions in V2.
no, I'm talking about 4 and 5. In what?
They didn't have self-transitions.
Oh, yeah, it would be like this one?
Yeah, that would be 2.
Yeah, definitely. Yeah, so the class containing states 2 and 3, they're aperiodic.
Oh, wait, you just said for transient state.
Yeah. Oh, okay. Yeah, actually, we can define it for transient states. Yeah. For transient classes, we can define periodicity, like this case. Yeah, why not? Yeah. Okay. This is another very important thing that we can do in Markov chains, where so I have a class of states in a Markov chain, and they are periodic. So the period of that each state in a class is greater than 1, and you know that all the states in a class have the same period. So it means that I can partition the class into these subclasses where there's only okay. So I have the I don't know. Okay, so so let's assume that D is equal to 3. And this is the whole thing is the class of states that I'm talking about. I can partition it into three classes in which I only have transitions from one of these to the other one. So there is no transition in this subclass to itself. And yeah, the only transitions are from one class to the next one. So this is sort of intuitive. So just looking at 3 states, if the period is 3, I can partition it in this way. Or I can have it like 2 of these in this case, where I have like this. You see, so there's a transition from this to these 2 states and from these 2 states to here and from here to here. But I cannot have any transition from here to itself or from here to here or here to here. Just look at the text for, but just, yeah, for the proof and illustration. But yeah, there exists this kind of partitioning. You should know that. Yeah, so if I am in a class, in a subclass, the next state will be in the next subclass for sure. So I know the subclass in which my next step is. And in 2 steps, I will be in the other subclass. So you know, and you know the set of classes that I can be in state. In D plus M. So the other definition that you can say is that, again, you can choose one of the states in a class that I talked about. So let's say that I choose a state 1, and I define SM. SM corresponds to that subclass. Are all the J's where S1J So I told you that I will have D classes, and I can define each class as like this. So this is all the possible states that I can be in ND plus M step. So starting from state 1, in nd plus m step, I can be in set of classes for some n, you know, so m can be big. But anyway, this I call this the subclass number m. So yeah, there are okay. So let's just talk about something. So I said that in order to characterize the Markov chains, I need to show you the initial state or initial state distribution. So it can be deterministic, like I start from some specific state all the time, or there can be some distribution like px0, meaning that this is the distribution that I will have at my initial state. I don't have it here, but using I think chain rules, we can easily find the distribution of states at each time instant by having the transitional probabilities and the transition probabilities and the initial state distribution. I just wrote it for you. So I need for characterizing the Markov chain, I just need to tell you the transition properties, probabilities, and initial state. So a very good question is that is there any kind of stable behavior when time goes, you know, when like in very far future? So so I had an example here, just looking at here. So this is a very simple thing that I can say about state, about this Markov chain. I know that in very far future, there is a 0 probability that I'm in state 6. And you know it why? Because anytime that I'm in state 6, I will go out of it with probability 1. So there's no chance that I will be there. Or yeah. Or I can say that if I start from state 4, in very, very far future, I will not be in state 1, 4, or 5, for sure. You know why? Because there's a positive probability of going out of these 3 states, like here. And then if I go out of it, I can never come back. So there's a chance of going from state 4 to state 2. And if I ever go there, I will never come back. So these are the statements that I can say about the stable behavior or the very, very future behavior of the Markov chain. So the question is that can we always say this kind of statements? And what kind of statements actually we can have? And so you see that, for example, for state 6 in previous example, I could say that the probability of being in state 6 as n goes to infinity is 0. So can I always have some kind of probability distribution over the states in future as n goes to infinity? This is a very good example. This is a very good question. And actually, it's related to a lot of applications that we have for Markov chains, like the queuing theory. And you can have queues for almost anything. So one of the most fundamental and interesting classes of states are the states that are called ergodic, meaning that they are recurrent and aperiodic. So so if I have a Markov chain that has only one class, and this class is recurrent and aperiodic, then we call it a ergodic Markov chain. So we had 2 theorems saying that if a state in a class is recurrent, then all the states are recurrent. And if a state in a class is aperiodic, then all the states are aperiodic. So we can say that some classes are ergodic and some are not ergodic. So if the Markov chain has only one class and this class is aperiodic and recurrent, then we call it a ergodic Markov chain. And The very important and nice property of ergodic Markov chains is that they lose memory as n goes to infinity, meaning that whatever initial distribution that I have for the initial state, I will lose memory of that. So whatever state that I start in or whatever distribution that I start in, after a while, for a large enough n, the distribution of states does not depend on that. So again, looking at that chain rule, I could say that I can find the probability distribution of xn by looking at this thing. And looking at it recursively, it all depends on P of the initial distribution. And the ergodic Markov chains have this property that after a while, this distribution doesn't depend on initial distribution anymore. So they lose memory. And actually, usually we can calculate the stable distribution. So this thing goes to a limit, which is called Pj. So the important thing is that it doesn't depend on I. It doesn't depend where I start. Eventually, I will converge to distribution. And then this distribution doesn't change. So for large enough n, I have this property for ergodic Markov chains. We will have a lot to do with these properties in future. So I was saying that this pj, pi j, should be positive. So being in each state has a non-zero probability. The first thing that I need to prove is that Pijn is non-zero for large enough n for all j and all the initial distributions. And I want to prove that this is true for ergodic Markov chains. This is not true generally. So well, this is more combinatorial issue, but there is a theorem here which says that for an ergodic Markov chain, for all n greater than this value, I have non-zero probability of going from I to j. So the thing that you should be careful here is that for all n greater than this value. So for going from a state 1 to 1, I can go it in 6 steps. And 12 steps and so on. But I cannot go it in 24 steps, I think. I cannot go it in I cannot go from 1 to 1 in 25 steps. But I can go from 1 to 1 in 26, 27, 28, 29, 30. So for n greater than n minus 1 square plus 1, I can go from any state to any state. So yeah, I think this is tight. This bound is tight for state 4. Okay, sorry. Maybe what I said was true for state 4. Yeah. So I'm not going to prove this theorem. It's well, actually, you don't have the proof in the notes either, but yeah, you can look at the example and the cases that are discussed in the notes. Is there any question? Fine.